Thank you, Alex, and thank you all for joining us for this virtual talk today. During this presentation, we're just going to give a brief introduction of some of the research that Cory Suski and I at the University of Illinois, as well as Dr. Allen Mensinger at the University of Minnesota, have been doing to try and find ways of coupling two already known to be promising deterrent technologies. In this case, that would be acoustic deterrents with carbon dioxide to try to create a more effective deterrent technology for big-headed carps. So again, this really shouldn't need any introduction for an invasive species conference like this, but again, the target species that we're looking at is big-headed carp. So again, these would be silver and big-headed carp, invasive carp from Asia. They were introduced out of Arkansas, got into the Mississippi River, and have been known to be very voracious feeders and can alter ecosystems once they've become established. And so the key on this is really try to prevent the establishment of these invasive carp. And in doing so, we know that they're currently moving northward through a series of locks and dams on the upper Mississippi River with their current reproductive front and lock and dam 16. And so we're hoping to use pinch points through the locks and dams to really slow their expansion. We already know that they're in Minnesota, but in very low numbers. So again, we're trying to slow the spread of these species so that way we can hopefully prevent their establishment and reproductive abilities. And to do that, again, we're going to utilize these locks and dams as kind of choke points. And the hope here is that we can apply behavioral deterrent technologies. In this case, I'm showing a speaker here that you could place in front of the lock chamber to hopefully deter invasive carps while allowing native fishes to pass. So again, we want to hopefully create a selective deterrent that would block the unwanted species while allowing some of these native fishes to be able to move upstream and allow to migrate into the areas that they need to spawn. And two of the promising ones that have now been looked at for the last few years in field studies at locks and dams is using just sound alone, in which case that's shown to be about 80 to 90% effective in laboratory studies, and it's currently being tested at lock and dam 19 with big-headed carps. However, there's another technology that couples this sound with an air curtain to create this wall of sound. And so what ends up happening is sound gets entrained within this air curtain, creating a sharper pressure gradient that in theory might be more effective at deterring carp species, especially in the laboratory, shown to be about 95% effective. However, with all of these deterrent technologies, there's always weaknesses that, at least in these real world scenarios, we want to create these deterrents to be as effective as possible at blocking wild fishes. And so the question we have is whether or not we can enhance these acoustic deterrents in any way. Again, knowing that no barrier is going to be 100% effective, but if we can target more than one sensory system within these target fish species, as well as potentially condition fish not just to be blocked by these deterrent systems, but also just avoid and not be near these deterrent systems to, again, try to minimize propagule pressure in front of these deterrents, this would potentially increase the effectiveness of these deterrents on big-headed carps. And so our solution to this is to try and pair acoustic deterrents with other noxious stimuli. And the stimulus that we have chosen, in this case, to try and couple acoustic deterrents is the use of carbon dioxide gas. In this case, there's a wide range of literature that has shown that CO2 can be both sensed by a wide variety of fish species, and that they not only just sense it, but they will also actively avoid CO2 in both laboratory studies as well as field studies. However, the concentration needed is relatively high in the 70 to 120 milligrams per liter of CO2 range, which can end up dropping pH to about 6.5 or 6 in that aspect. And so again, CO2 by itself has been shown to be effective, but we're curious of whether or not we can try to incorporate CO2 within other types of deterrent technologies to make them more effective at blocking and deterring carps. And so this led into our two-stage project here with Mensinger. The first one, which is being led by the University of Illinois, is trying to determine whether or not we can couple sound with, or basically couple CO2 to this sound and air current deterrent system, and determine whether or not adding CO2 might increase its effectiveness, while Dr. Mensinger is looking at determining whether or not he can condition carp to associate sound with increasing CO2 concentrations, such that pairing these stimuli would make acoustic deterrents more effective over longer periods. And so for this first part, we'll be going through this first project, which is, again, trying to determine whether or not we can add CO2 within a coupled sound and air current deterrent system to make it more effective. And so to do this, we really had three main steps. The first one was just determining whether or not we could optimize the amount of CO2 that we could put within an air curtain to actually block carp. And so that'll be the majority of what I'm talking about for this presentation. But after that, once we determined the amount of CO2 that we would need to block carp, we then went up to Minnesota this previous summer and actually looked at using CO2 within a coupled sound and air curtain deterrent system to see if it would indeed be more effective at blocking as well as deterring carp from that deterrent system. And so, at least for that first project where we want to determine the amount of CO2 that would be needed within an air curtain, we had three main research questions. The first was just determining whether or not adding CO2 to this bubble curtain would actually enhance its effectiveness. Will this even be a feasible option, or will, for some reason, CO2 actually increase passage across the deterrent? If it was effective at blocking passage, we wanted to get a sense of the amount of CO2 that would be needed within that bubble curtain to block carp passage. And then finally, we also wanted to know if carp would actively avoid the CO2 bubble curtain, because with these deterrent systems, we'd want it to also be actively avoiding these systems, so that way they were less likely to even be near it and be able to pass the system going through. And so to do this, we utilized a choice tank with single laminar flow at the University of Illinois. At the top right is basically the look of the choice tank that we're using. It's fairly small, and so we were only able to test fairly small fish in this setup. For this, we tested common carp with these and test them in groups of 3 fish. The way the singular laminar flow works is we've got 2 head tanks named as A and B that allowed water to flow through these baffles in area C, and then eventually this water flow would be straightened to be late laminar flow that would then go into that test area in that D spot, where we would then monitor the fish movement in that test area in D. That water flow would then go out, and so that way, when we place an air curtain, which is shown in that red bar in the middle there, we were able to create 2 zones, one that was upstream that had unaffected water by either the CO2 or the air, versus downstream of that air curtain that was either at high CO2 concentrations or had bubbles going through from that air curtain. And so in these experiments, we chose to expose fish to 4 types of deterrent technologies. One, we just had control and we looked at the movement when no deterrent was being placed. We then looked at just the bubble curtain with just compressed air. And then we looked at 2 different CO2 concentrations within that bubble curtain, one at 100 milligrams per liter at higher CO2 concentrations, which had previously been shown to cause avoidance. And then we also looked at a lower CO2 concentration of 30 milligrams per liter to see if we could potentially use less CO2 when it's coupled with an air curtain. And so what we've got here in terms of the testing protocol, on the right, we're showing a representative sample of what the fish movement was looking. This is at about 2 times speed. And again, we were looking at fish movement in the test area, either before and then after the actual air curtain was turned on in this case. And then we could look at the passages across the deterrent as well as kind of where the fish distribution was within that test arena. And so with these, we had a 45-minute acclimation, and then we did a 10-minute pre-test period where it was off. And again, we monitored fish movement during that period. Then we turned on either the air curtain or the CO2 bubble curtain for a 10-minute paired period at 2 different concentrations. And then finally, we had a 10-minute recovery period. And then we did this for a total of 10 fish or 10 groups of fish for each treatment. And finally, we analyzed, again, passage across the deterrent to look at blockage, as well as their distribution in the tank to look at deterrents from the air curtain. So what did we find? So in this case, the first one we wanted to check is whether or not common carp are actually just blocked by the bubble curtain itself. So on the left-hand side here, we've got on the y-axis the number of crossings of 3 fish within that test arena across that bubble curtain. In the control in the white bar is during pre-test, so about 30 crossings occurred across that middle portion. During the test period, again, when nothing was on, we saw increases in passes rates to about 40. However, when we looked at the air curtain itself, you can see in that black bar that we actually saw a reduction in passages when we turned on that air curtain to about 60% blockage from that air curtain, which is pretty indicative of what we've seen previously in laboratory studies, is that the air curtain is not a perfect deterrent system, but it can block about 60% of the passages in these systems. And so then we were curious whether or not adding CO2 to this would improve its effectiveness at blocking carp. And so using a high CO2 at 100 milligrams per liter of CO2, we saw that when it was coupled with this air curtain, we saw a significant reduction in passages when we compared it across the air curtain. So about 85% of the passages were blocked. So again, this showed promise that CO2 within a bubble curtain was more effective at blocking carp than just an air curtain alone. And then we were also curious whether or not the amount of CO2 mattered. So in this case, we actually tested a much lower CO2 concentration of only 30 milligrams per liter of CO2 and found it to be as effective as the much higher CO2 concentrations, showing that in theory, there's a synergistic effect between CO2 and the air curtain that makes it a more effective deterrent, such that when CO2 is used alone, you need to use about 100 milligrams per liter of CO2 versus when it's coupled with that air curtain, we can actually use much lower CO2 concentrations, which might be useful when we're actually placing this in natural environments. And then finally, our last question is whether or not carp actually avoided the CO2 bubble curtain in the first place. So in the top left is showing fish positioning over every 15 seconds over a 10-minute period. And what it basically shows is that these fish were occupying the majority of the actual test arena, not really favoring one side other than the other. When you add CO2 to the tank period in one test, we actually saw that the fish were again not passing that curtain, which is shown in the red, and we're actually spending most of their time up near the front where low CO2 water was coming in, or ambient water was coming in. So they were avoiding that CO2 curtain. However, we did see that it really depended on where those fish were when that air curtain was actually turned on. So when the CO2 curtain was turned on, the fish were found in the CO2 in the downstream zone. We actually saw that the fish were less likely to actually pass the air curtain, showing that their actual perception of that deterrent seemed to have changed to where they would actually stay in lower or worse CO2 waters rather than actually try and pass through that air curtain deterrent system. And so we saw that carp would actually remain in these higher CO2 waters than pass through the air curtain. And so in conclusion, we saw that the CO2 within the bubble curtain enhances its ability to block common carp, and relatively little CO2 was needed. And interestingly, we saw that common carp will actually choose to stay within a high CO2 zone rather than pass through that bubble curtain. And so in terms of next steps, at least in Illinois, we're going to test the impacts of CO2 on other native species as well. In this case, we're looking at catfish as well as some fathead minnow to determine, again, non-native or non-target species impacts. as well as doing these larger scale laboratory experiments, which we did this summer at the Minnesota Aquatic at MESERC. And again, we want to determine whether or not CO2 might enhance a sound and air current deterrent system. And preliminary data at least shows that adding CO2 within this air current does in fact enhance the effectiveness on big-headed carps to where we're getting about 94% blockage with a CO2 air current and sound deterrent system versus just the sound and air, which was 87% effective. But obviously this is just preliminary data and hopefully have more for next time. And so for that, I'll kick it over now to Al to talk about his portion of the study looking at conditioning of carp to sound.
Alex, can I share my screen?
Hi, you should already be able to. Let's see here. As a panelist, you should already be able to.
It says the other participant is sharing, so maybe Clark can move.
Oh yeah, Clark may have to end his share first.
Did you want me to end the share or did you want me to just click through the slides for you?
Well, I think I can start using my own slides so
Sounds
you don't
good.
have to click through them.
All right, I'll stop share.
Oh, good, there we go.
Thank you, Clark, for that update. The nice thing about MESARC is we have several investigators looking at the same solution to the carp problem using slightly different strategies. And my lab has basically focused on auditory sensitivity and bioacoustics in the big-headed carp. The advantages, as Clark has mentioned, to the bioacoustics is they're environmentally friendly, relatively inexpensive, and the carp react to higher frequencies that have less impact on native species. Negative is that these fish seem to habituate to the sound over the long term, and there is some impact on native fishes, such as the bighead buffalo can hear these high frequency sounds. So the solution was to pair bioacoustics with another negative stimulus to hopefully get a synergistic effect of both stimuli. And we've shown previously that sound's a very effective deterrent in carp. Here we have a pond on the left, split in two by a small channel. The carp will go throughout the pond. And then when we add sound, which is represented by color in the bottom, and the red color is higher sound, that blocks the carp from passing through the channel. And this works pretty well in both silver and bighead carp, but eventually the carp begin to ignore the sound. And so this is called habituation. And in this terrestrial example, you see that the scarecrow was added to the field. The crows were initially scared away, and then they realized the scarecrow wasn't doing any harm to them, so they came back, and you needed to put another modal response here. The scarecrow's moving, and that moves the crows away. And so that's the thought here, is to actually add two adversive stimulus so the carp are not habituated to one. And we go to the classic experiment of Pavlov's dogs, and I think everyone's familiar with that. It was where Pavlov paired a bell with food, and the dog was associate the sound of the bell with being fed, and then he removed the food, and we just got the dog to salivate with the sound of the bell. Well, what we're going to do here is use two very negative stimuli, sound and CO2 together, and the goal is to condition the fish to associate sound with CO2, and therefore make the sound deterrents much more effective after conditioning. We think this will increase the effectiveness of both deterrents and also allow us to use CO2 less frequently. And so, as Clark illustrated, the obvious point to do this are lock and dams, where we put sound and CO2 in the chamber or the approach. This schematic shows how this would work, is we would sonify the chamber, and then as the downstream gates open, add CO2 both to the lock and to the downstream approach, and pretty much have any fish in the area, there goes the CO2, associate the sound with CO2, and eventually, as they learn to associate this over several days or a week of conditioning, you would see that using sound alone would give the same effect, and you would only have to reinforce with CO2 on a weekly or maybe even a monthly basis. And we've been looking at two lock and dam structures, Lock and Dam 19 and Lock and Dam 5. Lock and Dam 5 is Minnesota, and we're very familiar with the vessel traffic and the soundscapes there, how long the downstream gates are open, how frequently they open. And so we've been able to recapitulate that schedule in the lab to treat the fish in a naturally relevant manner that corresponds with ship traffic. And for all those who are touring the lab tomorrow, this is what you'll see. We have two circular aquariums shown on the lower right, connected by a small channel. And this is a shuttle tank. And what this allows us to do is change the aquatic environment on one side of the tank and see how that affects the fish's behavior. And in this case, we're pumping CO2 in one side of the tank and hoping that the fish go to the other. And we have also added sound. So the black circles in the middle of each tank is a small underwater speaker. And the way this worked is that we would put the fish in one side of the tank, add CO2 and sound, condition the fish to associate the sound with the CO2, and then remove the CO2 and see how long the sound only would be an effective deterrent. And this is just an example. We have 5 small carp swimming on the left. We're adding CO2 to the left part of the tank, and you can see that the fish will quickly move from the left side to the right side. And this works both with sound, and it also works with CO2 plus sound. And here's some preliminary data. We have conditioned fish in red. These are fish that have been trained to associate sound with CO2. And we have fish that have not been exposed to CO2 in green. Silver carp are on the top, big head carp are on the bottom. And you can see that in both cases, by adding CO2, by just adding sound, that the fish will fairly rapidly vacate the premises. In the silvers, this phenomena seems to wane after about 2 weeks, where the conditioned fish no longer respond as well as the unconditioned fish. But with the big-headed carp, they continue to rapidly leave the chamber compared to the unconditioned fish. So our preliminary results is, as you guessed, carbon dioxide is a very effective deterrent. The interesting thing, and we've seen this in other experiments, that silver and big head carp display different reactions. And so again, a cautionary tale from our lab is that you have to look at both species of fish. You cannot treat them as the same species. Surprisingly, we saw fish actually have 2 strategies. We saw the fish quickly exit the chamber, but we saw a strategy we didn't expect. And these are in the conditioned fish that they would freeze in place and delay the exit. And this may account for some of the loss of time that we saw in the silver carp. And we saw conditioning lasted at least 2 weeks in the silver carp, and probably longer in the big-headed carp. Now, we know that small tanks are very problematic with sound, and I don't want to go into details for that, but this is the soundscapes of those small shuttle tanks. And you can see we're putting 140 decibels on the left side, and it lowers to about 120 on the right side. However, 20 dB sound gradient is not the best way to have the fish leave an area of high sound, because there's really no sound refuge. The sound is still pretty loud in the quiet end of the tank. And so to get around this is we built larger tanks. And again, if you visit the lab tomorrow, you'll see these in action. These are 2-meter round tanks connected by a 1-meter channel. And here we're adding, we're conditioning them with CO2 and sound. And we have a single fish in the upper right, on the right side tank that you'll see swimming. And then in the bottom right, a light will come on, and that represents the sound. And unfortunately, we don't have camera coverage of the channel connecting the two tanks. But eventually, in a few seconds, you'll see that fish swim to the quieter channel. And here it comes out of there. And so we found the bigger tanks to be much more effective than the small tanks, primarily because the sound gradient was better. So here we have 150 dBs on the left and 110 dBs on the right. And so this 40 decibel sound gradient provided a much better sound refuge for the fish to leave the channel and stay in the other tank. And this is data fresh off the press that was given to me by my student yesterday. And this is the big tank results. And if we just look at day 1 and day 3, which is the ones on the left and in the middle, we can see in the fish that were not conditioned to CO2 in the air types, that they return to the sound chamber much faster than the ones that were trained with CO2. And after about a week, however, this behavior started to wane slightly, and we're still analyzing this data. And so we saw some challenges. We knew these circular tanks would produce complex soundscapes, and the freezing behavior was unexpected. However, this may not be detrimental in the field, because if you can just imagine, if the fish stop swimming upstream by freezing, that the downstream current will carry them out of the lock. So this actually may be an unexpected bonus to this sound and conditioning. The positives, certainly, we allowed us to test many fish for extended periods of time, up to 28 days, determine the most effective CO2 concentrations and sound intensities, and it sets the foundation for future experiments. And we've been very fortunate for MASARC to provide an additional year of funding. And in collaborations with the St. Anthony Falls, we're actually going to make a mock lock and dam and test that in MASARC. This is a 5-meter by 3-meter tank. It's going to have a dam. It's going to have a functioning lock. It's going to allow us to put CO2 and sound in the lock, and we're going to be able to see whether in a much more realistic setting, rather than a circular tank, whether we can see how effective the deterrents are. And as an added bonus, all these studies have been done with, quote, normal fish. We're going to use motivated fish. We're going to have fish where we withhold food for about a week and then move the food to the upstream portion of the tank only, and we'll see if motivated, how effective these locks and or these deterrents are against motivated fish, which has been quite a pressing issue for many of the managers. And these are the people who actually did all the experiments. Jackie Collada is a master's student currently in my lab. Dr. Brooke Vetter is at the University of St. Thomas as a new faculty member, and she was kind enough to recruit a number of undergraduates to help. And Josh Schroppe is a master's student in my lab. So that's all I have. Clark, did you have any more slides?
I was done with mine. So yep, all good.
Okay, awesome. Thank you so much, Alan and Clark. I will remind all the attendees who've been listening to the presentation from these two gentlemen to throw your questions for them in the Q&A module at the bottom of your screen so that I can read them off as they come in. While we're waiting for our audience to provide some questions, I can seed some for us to get our conversation started. And I apologize in advance that I'm coming from a relative place of ignorance here, which might actually be good. So I might be asking easier questions than maybe our audience would ask. But I'd like to start off by asking if you can remind me, what is it that fish find scary or deterring about air bubbles? I still have a hard time wrapping my head around that. And this is for Clark or Alan.
So the air bubbles themselves, they'll create three different types of hydrodynamic or cues for those fish to respond to. It can either be a visual cue from the actual site of the bubble curtains themselves. The actual formation of the bubbles themselves will create low frequency sound. And obviously, fish, especially the carp species, are in tune to be able to detect, as well as the hydrodynamic, the flowing water from the actual bubble curtain itself. So at least in a lot of these studies, they've shown that under darkness, the deterrence properties are really due to the sound that's produced from the bubble curtains themselves. But again, the air curtain by itself is only about 50 to 60% effective at blocking those fish. So it's not extremely effective, but yeah, it can act in multiple ways and obviously impact other species in different ways, depending on either the visual aspects of the bubble curtains or the acoustical aspects of the bubble curtain.
Thank you, Clark. Alan, do you have anything to add to that?
No, that was an excellent summary.
Okay. We've got a question here from the audience. What would be the monetary cost do you expect a program that uses these types of deterrents to have perhaps at some relevant time scale, say a month or a year, if it were at a full scale deployment?
That's an excellent question, and we're just trying to sort out how often the CO2 would have to be deployed. But once you get the speakers in place, in the grand scheme of things, I don't have an exact price tag, but the speakers would be relatively inexpensive, and they certainly are good for about a year or two before being replaced. If you could automate it so that the speakers and the CO2 would open when the lock chamber gates open, you would not need very much manpower. I think it's an excellent question, and maybe Clark or Cory have a better idea of the actual cost of the CO2 injection system. I'm not sure on that one.
Clark or Cory, any weigh in?
I'll let Cory weigh in on that because I know he's helped out at least with some of the more larger scale field studies in a lock for CO2.
Yeah, so can people hear me, by the way?
Yes. Yep.
Cool. So I don't have I don't have an actual price tag on what a CO2 system would cost. But some of that work has been done. The lead on that was Aaron Cupp at Upper Midwest Environmental Science Center. And so there should be a report out on that. It's all kind of relative, but I mean, the cost of a CO2 system is relatively inexpensive. We still think it's a big price tag, relative to, going for coffee or something. But overall, the cost of the actual CO2 is low. You don't actually need all that much. CO2 is really cheap. And so, especially compared to, it's still, CO2 is still more expensive than say sound is always, because you just got, you got speakers and there's some infrastructure there. Whereas with CO2, you would need sort of like pipes and like delivery systems and pumps and compressors and those kinds of things. So it is more expensive, but it was not cost prohibitive, I guess is probably be the best summary.
Great, thank you. if anyone's got any additional questions in the Q&A, please send them our way. I guess I'm only going to ask a related question that I was wondering. So obviously sound, at a mechanical level, delivering that to a location, and then air, specifically CO2, delivering that to a location. I was wondering about economies of scale. Is coupling these two things difficult to do in a practical mechanical sense, or is it actually easier in some ways that if you have both systems, combining them in some way is convenient or easy?
Well, they're really two independent systems. The biggest problem, and I'm sure Cory and Clark would agree, is to avoid navigation hazards. We're working in a lock chamber, and obviously, if you could put the CO2 nozzle and the speaker right smack in the middle of the chamber, it'd be great, but it'd be run over by the first barge that went through. And so the challenge is putting these things in recessed areas where they'll still be effective enough. But just looking at some preliminary work, there's lots of infrastructures at the locks. There's power. There's a very good manpower to help you install these things. And so the infrastructure is there. You just have to buy some additional equipment, such as the compressors, and come up with a delivery system. But you don't need that many speakers, and even the large speakers that we're talking about are less than $5,000 each.
Okay, well, we're still waiting for some questions from the audience. I have one more for us. One question I would have, thinking about, say, having a speaker at a lock for an extended period of time, is, are fish going to get sort of used to the sound that's being produced, and maybe that deterrent effect would be reduced over time? Is there a mechanism, or have you folks been exploring a possibility of varying pitch, frequency, wavelength, sort of adjusting the sound deterrent to keep fish sort of deterred by that sound? Or is that not as much of an issue as you might think it would be?
No, that's an excellent point, and they are doing that in Lock and Dam 19. They have several different types of sounds that they use to prevent the habituation. And maybe Clark can comment. I know it may be proprietary, but I think the bubble curtain also changes their frequencies and intensities as they go when they're deployed.
Yeah, at least for the proprietary one, the one we've got doesn't change right there, but the actual signal itself is variable enough to where it reduces the chance for habituation to occur, at least in theory. But again, with all of these, no matter what, yeah, you want to minimize the chance of habituation, but that's also where coupling with other types of deterrent technologies might offer a better option in terms of extending the usefulness of these rather than just varying the actual sound source itself. But of course, always just will depend on what the overall goal in terms of the managers are, in terms of, are you trying to stop 100% of these carp from coming through, or how important is native fish passage and those sorts of things to determine what types of deterrent. Because again, as Cory and Al has seen, CO2 is a very effective deterrent, and more than likely will impact most species equally. And so you've got to be thinking about kind of your management goals moving forward.
Great. Well, awesome. Thank you for answering my questions as well as those from the audience.